Continuing on here in section 4.7, quadratic equations can have two real solutions, one real solution, or no real solutions. And we can use part of the quadratic formula to determine how many solutions a particular equation will have. If you look at the take note on page 242 to 243, the discriminant of a quadratic equation in standard form is the value of the expression b squared minus 4ac. It's the part that's underneath our square root. So, if the discriminant is positive, there's going to be two real solutions and two x-intercepts. So, it's either going to be a happy face parabola with two x-intercepts or a sad face parabola with two x-intercepts. And again, if that's if our discriminant is positive, because then we would actually have the plus or minus part of our quadratic formula. Okay, if the discriminant is 0, there's going to be one real solution and one x-intercept. That would be if our vertex is on our x-axis. Either there's a happy face or a sad face. I didn't quite get either of those there, but we'll pretend. Okay, so if the discriminant is 0, there's going to be one real solution and one x-intercept. Because what happens there is if our discriminant is 0, we don't need any of this plus or minus part of our square root, and we just get one answer. And if the discriminant is negative, there's no real solutions and no x-intercepts. On a graph, okay, we'd either be completely above or completely below. No x-intercepts and no real solutions, because we can't take the square root of a negative number and get real solutions. Okay, square root of a negative number isn't going to give us a real number. Okay, so there's going to be no real solutions and no x-intercepts. And again, that's shown in the take note box on 242 and 243. So here in example 3, we're going to use our discriminant to figure out the number of real solutions of this equation. So we're not actually going to solve it, we're just going to figure out how many solutions we would have. And this is helpful to help us determine whether or not some situations are possible, and we'll get to that in the next example. But for now, we're just going to figure out how many solutions, real solutions, we're going to have. So again, we're going to use our discriminant. In order to do that, we need to pick out our a, b, and c value, just like we did when we found our quadratic formula. The only difference is here we're just going to use our discriminant, which is the b squared minus 4ac, the part underneath my square root. So negative 3 squared minus 4 times negative 2 times 5. Negative 3 squared is 9. Here I get positive 40, which gives me 49. I look at this. This is a positive 49, which is going to give me two real solutions. Here's a way I remember. Positive gives me 2, 0 gives me 1, and a negative number gives me none. And it's not quite perfect there. But positive is going to give me 2. 0 will give me one real solution, and a negative will give me none. Now, what's the number of real solutions of each equation? Well, again, we're going to use our discriminant here. b squared minus 4ac, the part underneath our square root. A is 2, b is negative 3, and c is going to be 7. So, negative 3 squared minus 4 times 2 times 7. I get a negative number here. So, since it's negative, that means none. What's my number of real solutions? 0. I'm not going to have any real solutions here. And feel free to give this one a try if you'd like. Before we can find our discriminant, we need to have it set equal to 0, just like if we were going to solve it. So I'm going to subtract a 6x and subtract a 5. It doesn't matter which way you move, guys. I just usually like to make my x squared positive. So it doesn't matter which way we move. Some of you probably moved your x squared to the other side since that's only moving one term. That works too. Here, my a values are going to be 1, negative 6 for b, and negative 5 for c. If you moved it in the other way, then your signs would be opposite. You'd have negative 1, positive 6, positive 5. And again, we're looking for how many solutions. So I'm checking my discriminant. b squared minus 4 times 1 times c. This right here, two negatives, make this a positive 20, and I get to 56. Since this is positive, I'm going to have two real solutions. And again, that discriminant is helpful. We can always find that first, and then if we have solutions, we can plug it in to our equation to solve, because we need to find that number anyway. Keep in mind, if I was going to solve now, I would take the opposite of b plus or minus the square root of my discriminant over 2 times a. So I'd have my solution here. I'd want to reduce this if I could. But we have to find that number anyway, so we might as well find it first, because if it's negative, we know automatically we're not going to have any real solutions. So we can stop right there. Example 4. You hit a golf ball into the air from a height of 1 inch above the ground with an initial vertical velocity of 85 feet per second. They took all that information and plugged it into this function for us. The 1/12 is our height, that 1 inch, so 1/12 of a foot. 85 is our initial vertical velocity, and that negative 16 has to do with gravity. It models the height in feet of the ball at time t in seconds. So they took all that information and plugged it into our function for us. Now, we want to know, will the ball reach a height of 115 feet? So this 115 feet, that's our height. I'm going to plug it in there. And then use my discriminant to determine whether or not we have solutions. If there's solutions, that means it's going to happen if there's real solutions. If there's one real solution, it means it'll happen. If there's no real solutions, it means this will not happen. So rather than solving this entire thing, which has got some kind of wonky numbers here, let's go ahead and just find the discriminant. We don't care when it happens, at what time. We just want to know if it happens. And here I just combined like terms there. I took 1/12 away, so I'm left with 11/12. Okay, so my discriminant, first I find my a, b, and c values. Then I plug them in. B squared minus 4 times a times c. 85 squared is 7225. When I do all this, I get negative 7354.6 repeating, which is going to give me a negative answer, which means I have no real solutions here. This doesn't happen because I don't get any solutions there. Okay, so is the ball ever going to reach a height of 115 feet? Nope, because when I plugged in this height, I got no solutions. Okay, there's no time at which that would happen. No t value means there's no time in which that would happen, and our height is never going to be 115 feet. Now, for you to pause here and give this a try if you'd like. Without solving the equation, will the golf ball in example 4, so using the same equation here, ever reach a height of 110 feet? So we're going to do the same idea here, but with 110 feet. So, first thing we're going to do is we're going to plug in our height. And see if there's a time where that happens. Is there a solution here? So we have to get it set equal to 0. And again here I'm just going to add on that 1/12, which gives me 11/12. So my discriminant, now that it's set equal to 0, I find my a, b, and c. And my discriminant is b squared minus 4ac. So 85 squared minus 4 times negative 16 times negative 109 and 11/12. Which gives me 7,034.6 repeating. I don't even need to subtract here, I just need to know that my answer is going to be positive, which means I would have two solutions. So there's 2 times when the ball would have a height of 110 feet. So will it reach that height? Yes. Somewhere on the way up and somewhere on the way down, it would have been 110. But it never actually gets to 115. So it's pretty close to 115, just never actually gets there. And again, because it's positive here, we know there's going to be 2 times where that ball reaches that height. And so yes, it will reach. Quick recap here. A quadratic equation, ax squared plus bx plus c equals 0, can be solved by a formula that gives values of x in terms of a, b, and c. The real solutions of a quadratic equation show the zeros of the related quadratic function and the x-intercepts of its graph. And that's all I have for section 4.7.